Hello, I'm David Hughes, and welcome back, everybody, to this next one-hour session to continue the discussions on non-horizon scale imaging and the additional high-impact science that we can conduct with the enhanced capabilities of the ngEHT. We will have three very interesting talks of approximately 20 minutes each. I'll give the speakers a 5-minute warning so that they can wrap up their talk and then have the opportunity to respond to any questions for a few minutes. And for the audience, if you wish to ask a question, as always, please use the raised hand function in the Zoom chat or write your question into the Zoom comments. And I remind you that these talks will be followed by a 30-minute discussion session moderated by Jose Gomez. Okay, so let's begin with the first talk from Neil Nagar from the University of Concepcion. Neil, please.
Thanks. So I'm sharing now, so presumably you all see it. So effectively, thanks for the opportunity to talk about this. This is about a sample of galaxies to be observed with the EHT and the ngEHT. This is work with primarily Venkatesh Ramakrishnan, a postdoc here at UDEC. A huge cross-section of many of the EHTC members who've been contributing a lot, and more recently the Titans group in Chile, which I'll mention later. So, oh dear, I've lost my mouse, I'll be right there. Yeah. So we've all heard what the ngEHT can do in M87. It'll make the image on the left to the image on the right. But as I mentioned here, we're trying to see is what science can we get if we do tens or hundreds such images. And the motivation, of course, is clear. There could be more black hole shadows, more accretion flows, and more jets. And more importantly, this would be over a very large parameter space, varying mass, varying spin, varying accretion rates, different kinds of jets, or the absence of jets, orientations. And it also opens a lot of new transversal goals. Better black hole mass estimates can recalibrate the M sigma. We just heard all about subparsec binaries and some cosmological parameters. So where are we currently with the EHT? This is a figure we'll see a lot. So on the x-axis is the ring diameter. Remember that's 10.4 Rg, larger rings to the right. On the y-axis is the brightness, the estimated 230 gigahertz flux for the EHT in Janskys, and brighter objects to the top, of course. And the red dots are all sources that have been imaged or are being imaged with the EHT currently, have been observed with the EHT currently. The Salmon region is important. That's, of course, the rightmost. Those are the large rings. Given the EHT resolution, that's where you can resolve the ring, as we all know in M87. The green region is where you can resolve the base of the jet at better than 100 parsec, at better than 100 Rg. And so what you see is, of course, what we all know. There are two salmons and there's no green. And in a way, that's kind of disappointing, right? Now, it's always been known by the EHT founders that there are more objects, but we haven't pursued this very, very comprehensively, and that's the point of this presentation today, to hopefully convince you that there are lots more objects. So we need more x-axis values, more ring sizes, we need distances and black hole masses. We need more y-axis values, which is VLBI, high resolution, high frequency fluxes. So here for the x-axis, we just have this big catalog of black hole masses. Recall that there are only about 200 measured black hole masses, but the rest are all estimations. M sigma, M bulge, real reverberation mapping or single level reverberation mapping, lots of fundamental planes, they're all just thrown in here. And in the figures, you see the distance or the redshift on the x-axis to emphasize both the low and high redshifts. And on the y-axis is the ring size, right? This 10.4 Rg size. And so you can kind of identify individual samples. Red symbols are measured black hole masses. Blue symbols are estimated. The horizontal lines I'd like to talk about, that's the black horizontal line labeled EHT. Anything above that line, we can resolve the ring. Anything above the blue line labeled GEO, the blue horizontal line, we could resolve if we add an orbiting antenna in geostationary orbit. Anything above the red horizontal line marked L2 is things that we can resolve if we put a EHT antenna in an L2 orbit. In Earth, a Sun-Earth L2 orbit. And so it's just kind of a leading thing that, yes, there are very few objects today, but these could be expanded. For the y-axis, of course, we want VLBI detections and we want them at high frequency so that we know we can detect them with EHT. So here we have this big VLBI catalog. It's basically all EHT observations, all GMVA observations, specifically NIRE, and literature, other individual sources, and very large samples, including the VLBI catalog, the calibrator catalog, the radio frequency catalog, individual literature. And we've been working a lot over the last years. Venkatesh Ramakrishnan leads this, pushing to higher frequencies on already detected VLBI sources and starting new campaigns. And what we get is here on the right. Of these 14,000, if we just cut it down to only those detected on long baselines or peak fluxes in high resolution maps, and only if we extrapolate the flux to the EHT and we get greater than 20 millijanskis to be a reasonable detection limit, that's the kind of numbers we have. We have more than 5,000 sources which are detected with VLBI at 8.4 gigahertz or higher, and which extrapolated to the EHT would be 20 millijanskis or brighter. And then as you go to higher and higher frequencies, they're fewer and fewer because many of these have not yet been observed at high frequencies. Until you get to GMVA, there are only about 270 of these, which are then relevant for the EHT and which we already know are very compact and very bright at the GMVA, therefore detectable with the EHT. So effectively, putting all this together, clearly, this is a reasonably big sample, but I'm often asked about the spectral indices of these VLBI sources. It's a mess. Frequency on the x-axis, normalized flux on the y. I've just cut it to 8.4 gigahertz to GMVA, otherwise it gets too messy. You can see there's just a whole slew. These are different resolutions, different epochs, and AGNs are variable. And very roughly, to give you an idea, the black solid line is a spectral index of -4. I'm actually using -0.2 plus specific factors for increasing the resolution, which actually statistically fits most of the sample, right? So now we have to put them together. What is the intersection? All of these VLBI sources and all of these black hole mass sources. It's very disappointing. You put them together, you only have about, thinking of only these VLBI sources, which are presumably bright at the EHT, only about 1,000 have redshifts and only about 800 have black hole masses. If we further cut that down to only those with a ring size, which is reasonably big, 0.01 microarc seconds, we have about 200 to 300 galaxies, right? So effectively what this tells us, and without a redshift. So that, of course, and this I introduced because just to say all the results I'll present from now on are very much in progress because we've only caught about 10 to 20% of the sample. There's lots more to add into it. That's one of our major jobs over these last years, is getting, for example, black hole masses and detected sources. This is a huge task. Several students here working on it. Of course, redshifts are easy, databases, archives, and then proposing for new data. Black hole mass estimates, we're just working through the standard, again, using databases, archives, and new data, the standard M sigma, M bulge, fundamental planes. One of the more promising ones, for example, is the radio, X-ray, and black hole mass plane. It has a big scatter, but why it's very relevant, of course, is E Rosita, which will give us hard X-ray fluxes for most of these AGNs, and SDSS-5, which will do multi-epoch or single-epoch reverberation mapping on many of these E Rosita sources. So we're already working on this. We hopefully will have very many more to ingest. Of course, finally, we want black hole mass measurements and not estimates. And so the very best targets, we're just going up this pyramid, getting redshifts, then the best ones we get estimates. And then finally, we are trying to go to ALMA and MUSE to get a real black hole mass for the most important ones. In fact, related to this, yesterday we got our M87 MUSE AO data set delivered. This is stellar and gas kinematics all in one cube, very high signal to noise. So hopefully we can also start to work on this disagreement between emission between ionized and stellar black hole masses. On the right, we also want to increase the number of VLBI sources with high frequency VLBA. So again, we're going up the pyramid. Low frequencies, we go to 43 gigahertz VLBA, we go to GMVA, and eventually we come to EHT. All of this again led by Venkatesh Ramakrishnan. So we're going to make that innermost blue circle as big as possible, and we're going to increase the intersection with black hole masses and redshifts. And that's, so from now on, we are seeing about a fifth of the sample that we have already, and we will be beefing it up. So just some examples, lots of VLBA observations, black contours are old, low frequency observations, red contours are 43 gigahertz, very bright nuclei, double-sided jets, things that are quite different from M87, low luminosity AGN. So let's come back to populating this graph, ring diameter versus brightness. The limitation was several-fold. One of the main ones was that the source had to be more than 500 millijanskis at ALMA for ALMA to phase up into the EHT. And that was the main limiting factor. This requirement has been removed because of phase reference phasing at ALMA. And so this coming cycle will allow observations of sources that are only a few tens of Jansky at ALMA resolution. They can phase up on a nearby phase calibrator, and then we do EHT with them. So we're hoping to go to 50 to 100 accessible sources, and then with the ngEHT, maybe 500 to 1,000. So what does this look like today? With all this extra data we've gotten, remember, we just have a small fraction, 300 new galaxies. We expect hopefully 3,000. We're still working on it. Here's the ring diameters and the brightness. The same figure again. Once more, the salmon region is where we can resolve the ring. The green region is where we can resolve the base of the jet at better than 100 RG. And you see several things that have come in. They look faint on the y-axis, but these are well accessible because of phase reference, phase up at ALMA. The red, of course, is those already done. The blue is things that we already have high frequency VLBI, so they're ready to go on. They're ready to go to the GMBA plus ALMA and EHT plus ALMA. And in fact, we've submitted proposals for this. The cyan are slightly lower frequency, less than 43 gigahertz. So we first have to get them to 43 gigahertz, select the best, and then move on to the EHT. But things are populating. And now the vertical, no, we won't talk about the vertical lines yet. I should mention that circles are black hole measurements, triangles are black hole estimates. And so they will move around. In fact, 3C371, which you see up there, looks so promising, quite high on the graph. It actually has to come down because nominally, this was a mistake I noticed. I used the total VLBA flux at 86 gigahertz. I now actually should be using nuclear VLBA flux from the Lee et al. Paper. It may move to the left because this black hole mass is from a fundamental plane in Wu and Uri. Some sigma measurements suggest a smaller black hole mass, but we're looking into this. But the basic idea is there are lots more sources. Now, the fun thing is if you start to go to, if you put an EHT antenna in geostationary orbit, the salmon region increases, our resolution goes up. Everything in the salmon region can now be imaged. The ring can be resolved. And everything in the green region, the jet base can be resolved. Now we have maybe 10 galaxies, assuming also for a few future ones that move in here, 10 galaxies that could be where we could get black hole rings resolved. If you do an L2 orbit EHT antenna, things go pretty crazy. Of course, you have to increase the flux limit, but now you start to resolve a lot of rings, black hole rings, and you pretty much resolve everyone's jet at better than 100 Schwarzschild radii. This is just how this looks again in, now I showed this plot before, but this is only for the VLBI detections. But here I put the y-axis is the ring size, the x-axis is distance or redshift. The main thing to emphasize here is anything above the black, blue, and red lines will be resolved. Their rings will be resolved. And I really wanted to emphasize the right figure where you see that you can go out to redshift 2.5 in some cases, and in an L2 case, still resolve the ring. And that's pretty good. Now, of course, as I said, this is in progress. I mean, just as an exercise, we have a lot of sources with redshifts, but no black hole mass estimates. While we're working on it, I just assume that these sources only for the GMBA, the ones that are ready to go to EHT, so a very small subset, about 160 of them ready to go to the EHT, don't have a black hole mass. Let's assume an M87 black hole mass and just stick them on here. It gives you a first idea of how promising it could be, right? They'll move around depending on their black hole mass. An M87 black hole mass is optimistic. It gives you an idea that we will start to populate this space very much more, right? There's also this, everyone brings up this fact, why is there this big gap between M87 and Sagittarius and everyone else? Well, there are black holes that are large. Here's just an idea. Well, I call them 10 of the largest black holes, rings, but which have very low millimeter flux. The 11th is the first one, which I leave in for fun. It's a very large sigma, so Kai and Gultikan said he looked into the data to find out why it was published with a sigma of 921 kilometers per second. But what you see in the ring is ring sizes between 52 and 14, and there are many more just below this. These are intrinsically resolvable right now, but their fluxes are very low. So some of them are promising. Here's 1407, 1600 just as examples. These are old radio jets, but the nucleus right now is not active. So of course, what we need to do is, some of this data is very old, some of this radio data. We need to reobserve them, we need to monitor them. If we have a slight flare, we could actually do this right now and get more rings. But many of you might not be interested in on the horizon. We just had this extremely interesting talk just before this by Sarah. This is what if we just leave out the horizon idea, and for example, for binary black holes. And the fun thing about the 20 micro-arcsecond resolution of the EHT is effectively it's a sub-milliparsec resolution across the universe. So I've just dumped a few to not make it too complicated. Linear resolution on the x-axis, which is in parsec. You see it starts at milliparsec and goes down to microparsec. I've left Sage star off because it's just way off to the left. And the estimated 230 gigahertz flux on the y-axis. Circles, let's see, circles and triangles. Circles have black hole mass estimates, triangles don't have black hole mass estimates. And the color is by the redshift. So what you see is there's a reasonably large already, even with our 300, at this point, 400 galaxies, there are a large number of milliparsec separations that can be probed with the EHT. In the special case that we find two lit up black holes orbiting each other. And we have thousands more to be put in here once we get their redshifts. Typically, they'll fall between 10 to the minus 4 and 10 to the minus 3 parsec. Because to be further to the left, you really have to be close by, and in which case you have a redshift and you have a black hole mass estimate. So the ones that we're slowly populating here typically fall milliparsec to 0.1 milliparsec, but the numbers will increase to thousands there. So it's really, really very promising. Of course, there's a lot of work going on, observations in theory. A lot of this led by Venkatesh, but also some part which I've mentioned now with the Titans. Lots of VLBI observations, multi-frequency monitoring, a lot of...
sorry to interrupt, 5 minutes.
Yeah, I even finished before that actually. Thanks. And some simulations and theory. Talking about simulations and theory, so we recently started, because that's a lot of work here. Venki's triplets, he does a lot of work, but of course we need a whole team. We've recently renewed our earlier funding to a slightly larger funding opportunity in the nuclear millennium called Titans. This is we've started very recently, 2 months ago, between 4 universities in Chile. And we're doing black hole formation and EHT predictions in the theory and simulations group. You will hear talks of these from Benisha Bandyopadhyay and Dominic Schleicher on Thursday. We do black hole growth a lot with STS's 5e Rosita and other large samples, which then helps the ether sample to get black hole masses. And of course, we work on ether and related things for black hole imaging. There's also a technological component, which is mainly high bandwidth satellite communications and helping with ngEHT sites into the future. There are also longer term planning between a larger group in Chile about starting some sort of Chilean National Observatory, radio observatory, starting with perhaps participation in the APEX telescope, maybe then the LCT telescope. And if ngEHT dishes come to Chile, then we could try to operate them. And so in summary, basically, what we're building up, and we're still in the beginning, the results already very promising, as I showed you. We're still at the beginning, we're building up this definitive sample for EHT science. At this point, this is not science-based, it's your logistic blanket upon which, knowing the numbers, you can decide what science you can do with it. And it's also important to do this early because apart from thinking of the science, it's also going to drive some of the technological requirements we want from the EHT. You know, knowing how many sources and how bright they are and what size their ring is really will help you decide what sensitivity we need, what resolutions we need, whether we need to go to space or not. So of course, there's all kinds of science, rings and jet bases over parameter space, coming to a point where we could get hundreds of black hole rings resolved and therefore hundreds of black hole masses, sub-milliparsec binary black holes and lots of others. So what's in progress, what we have is we probably can do 50 for the near horizon science, and we could get to 500. If you look at non-horizon, we easily have 1,000 in the sample. So we're not going to be limited by targets for the ngEHT in large part. Of course, this is statistical, we still have to find out, but it doesn't seem likely. Rather, we're going to be time limited, and so we really need optimized strategies. And of course, there are lots of optimized strategies. As you know, just UV coverage, UV amplitude plots. As you know, different a ring, a disk, a jet gives you very different UV amplitude versus UV plots with certain priors and with heavy load lifting done by the GMVA, for example, so that we can get some priors. One doesn't necessarily have to image these objects to get black hole mass measurements. The same thing with binary black holes. This here, there's an example of what closure phases look like from an orbiting hotspot around a supermassive black hole. You can change the scale and make it a binary black hole. And what we're looking at is maybe something like an LSST, where repeated snapshot observations spread over time of a lot of these targets can then eventually be combined into an average image, but then in the middle, can be looked for time varying factors and black hole mass measurements. So we're always promising this paper, but it's always tempting to add more and more, but we're just going to have to snip it. Venkatesh will send this out around mid-2021. I keep changing the date, not because we're not ready, but we just try to keep adding more, and then with our graduate students, we'll start with segments. That's it. Thank you very much.
Okay, thank you, Neil. Unfortunately, we only have 1 minute for questions. So if anyone wants to ask a question, please raise your hand quickly. Otherwise, I can go to a couple of questions in the chat. Okay, I don't see any raised hands. So there was, and we don't have time to go into all of the questions in the chat. We can pass that over to the discussion session. But from Maciek and Eduardo, there was some question over the precision of the fluxes. Perhaps we can actually leave that to the discussion session, since I think that will take too much time here. Just trying to see some, still no raised hands. So from Gopal, all your plots with green and orange bands seem to be based on the 230 gigahertz resolution for ngEHT. Is this correct? If so, you're going to be able to go to 345 gigahertz and higher. Does your, if you are able to go to 345 gigahertz and higher, does your sample size get larger?
Well, I could say very quickly, yes, we initially went for 230 gigahertz, but and it's a long way to extrapolate from 86. So I'd be worried to do that right now. We were from the CHT snapshot imaging for a few of these, and we'll probably get better statistics to understand this better. And instruments like KVM and some Venkatesh programs, which are doing simultaneous spectral indices on some of these, will help us clarify that. So it's a good point, but we don't know yet. Okay, well, there's a number of other questions in the chat, so I'll try and keep tabs of those and pass them to the discussion session that will be moderated by Jose. So thank you, Neil. Thank you very much. And let's move to the second speaker, which will be Silke Britzen. Please go ahead, Silke.
Thanks a lot. So does this work?
Yes, it does. Yes.
Okay, thanks a lot. So hello, everybody. Thanks for this exciting conference, and I'm very happy about the invitation to present this talk. So we are very much amazed about the results we found out for an AGN emitting high energy neutrinos. And we think that these high energy neutrinos are somehow a spotlight with which we can probe very fascinating AGN physics. And of course, what we found can be done much better with the ngEHT in the future with much higher resolution and precision. But I think what we find will be of interest for ngEHT observations. And at the end of my talk, I want to come to an underappreciated feature of AGN physics. And I think this will help in future ngEHT observations. So I would like to take you to the South Pole, to this beautiful ice cube facility, which is sitting on top of the ice at the South Pole, and it's sitting on top of an array of photodetectors which are frozen in the ice of the South Pole. And this facility captures neutrinos so energetic that they must have originated outside our solar system. And how does this work? I want to show you a simulation of this. So a neutrino enters the ice. It rarely interacts with matter, but if it does with the ice cube molecules, then charged leptons can be created and they propagate through the ice. If they're very energetic, then with a speed of light, a speed larger than speed of light, and they emit Tetarenko radiation. And this Tetarenko radiation is being detected by the photomultipliers frozen in the ice. And this signal is then digitized, and from this signal, you can deduce the energy of the incoming neutrino and the direction from which it is coming from. And this is a very important point. So the origin of these neutrinos are thought to be, for example, black holes, the vicinity of black holes, so AGN, supernova remnants, or gamma ray bursts. I want to focus on the AGN, of course, for this talk. So there are more messengers which are coming from the inner parts of AGN. In particular, these are these gamma rays, which are indicated here. So they point to their origin as well, but they can be absorbed, and they are created in multiple emission mechanisms. So it's not so easy to figure out how they are created. Then there are, you see these red loops down here. These are cosmic rays. They come from a similar origin or the same origin as the gamma rays, but these are charged particles and are deflected by magnetic fields, so they lose the memory of their origin. What's really great about neutrinos indicated here with this green dashed line is that they are weak neutral particles that remember where they come from. So they point to their sources and carry information from deep within their origins. But of course, there's a connection and there's a partnership to explore between gamma rays and neutrinos and cosmic rays. So the interesting point now, there is a partnership between gamma ray production and neutrinos, but from the 2,863 blazars monitored by Fermi, only 3 AGN have been identified as likely neutrino emitters so far, only 3 as far as I know. And the question now arises, what is so special about these AGN? And this is, I think, a very interesting question. And I saw this as a rare opportunity to learn something new about jets. So it's like we are using neutrinos as tools to probe AGN jet physics. And this is teamwork. I'm very happy about this collaboration and list my co-authors here. I think it was a pleasure and is a pleasure to work with all of them. And I think we are all happy about the many results we produced for this source, Parks 1502 + 106. The question, is it a ring accelerator? Unusual jet dynamics in the ice cube, candidate Parks 1502 + 106. And I'm very thankful to the anonymous referee. The paper is accepted for publication in monthly notices as of today. Okay, so there is a special coincidence. The ice cube neutrino 190730A coincides in the position with Parks 1502 + 106. And this source is, you see an image up here from the Mojave webpage. Parks 1502 + 106 is the 15th brightest gamma ray source in the sky at energies above 100 MeV. And it's at a large redshift. So this in itself is untypical. At a redshift of 1.84, so extremely high intrinsic luminosity can be inferred from this. It's highly variable in the gamma ray band. It has an estimated neutrino energy of 300 TeV, which is interesting. And it's a broad emission line flat spectrum radio quasar, which is highly polarized. This source has been studied across the electromagnetic spectrum by many colleagues so far, but we had a closer look what's going on in this source. You all know the sketch of the inner part of an AGN, the inner regions of an AGN with the black hole, the accretion disk and the torus, and the jet, which is shown straight here, but I think most of us know that a jet is rarely straight. What is also indicated is the broad line region here and the narrow line region, because they play a role in what I'm going to tell you. So we had a look at the jet based on the Mojave data. We reanalyzed and remodeled them. And what we found is really not a straight jet. I show you what we found in the VLBI data. So there is a curved jet, but in addition, we find a ring structure within the jet. I have never seen something like that before, but I think it's very fascinating to find such a structure where we only expected a jet. So if you have a look at one epoch of the Mojave data, you already see that something is going on there. So this is the jet, and there appear components which really do not belong to the jet. They appear at different places, positions where they are not expected. And if you have a look at all the 13 years of data, beautiful data by the Mojave team, then you see that we do not only find a curved jet, here shown in green, but we find this ring structure around the jet. And with model fitting, we could determine all the parameters of the individual features of the jet and of the ring structure, determine apparent speeds, and look at the position angles. And we also had a look at the polarization data. And this is really, I was amazed to see this. You see the polarization information here on the right, and you see these black spots here, which indicate very high polarization. And again, this coincides with the position of the ring. So these ring features are highly polarized. We had a look at the evolution of the jet components with time and of the ring features with time, and we find evidence for precession. We find two periods in the radio light curve, 3.4 and 13.4 years. And this fits nicely to the kinematic data. The longer time scale can be associated with jet precession, and for the shorter time scale of 3.4 years, this looks like what we found for OJ287. So this could be a nutation. The idea we come up, this is a model, collision cloud model by Michal Zajacek, everything in one sketch here. So this is the central, probably supermassive binary black hole, and a curved and precessing jet, and an interaction by the curved and precessing jet with the surrounding narrow line region clouds most likely produces this ring feature. So this ring which evolves with time. So it's an interaction of the curved and precessing jet with the narrow line region clouds. There is more. We've also found evidence for spine sheath scenario in Parks 1502 plus 106. You see a sketch here on the left. So you have a layer outside and a faster spine inside, and the ring reveals the sheath and its interaction with the surroundings, with the clouds. And it provides an external photon field. And in the context of the quasars, the external photon field can support the external Compton emission beyond the broadline region and thus the torus scale. But this spine sheath scenario also supports the generation mechanism for the neutrinos. So in terms of particle acceleration, this scenario is important as well. So non-gradual shear accelerates electrons and protons at the jet boundary, and gradual longitudinal shear acts in the inner part of the jet with an efficiency decreasing with the radial coordinate. So this scenario predicts a larger concentration of energetic particles towards the jet boundary. So if you put all the pieces together, we got interested in the source because of the neutrino emission and the result by IceCube. Then we found this ring emission around the jet in based on the VLBI data. Based on Sloan Digital Sky Survey data, we find evidence for outflowing broadline region material. We put together a very nice light curve, and I would like to focus on this a bit. So this is radio data in blue and gamma ray data in magenta. And I tend to say that this looks pretty regular up till 2014, and then there is an additional component in the, so there is flux coming from the core region, and here in red, the red line indicates the neutrino emission. So we have analyzed this light curve and all the other data, and the best model we can come up with is that this ring is created by an interaction of the precessing and curved jet with clouds from the narrow line region. The outflowing broadline region provides the external radiation field for gamma ray production via external Compton scattering, and the spine sheath scenario plays an important role because it supports this EC emission beyond the broadline region. The energies are sufficient to produce neutrinos via proton-proton interaction, and in the case of flaring activities and episodic encounters of the jet with dense clouds, the PP process can be efficient. Based on the gamma ray variability timescale, we constrain the gamma ray emission zone to the broadline region and within the jet launching region, and this finding is independently supported by SED modeling by Xavier Rodriguez et al. So this point is now, I think, the most important of all. We found, based on our analysis, a superposition of deterministic and stochastic processes in the light curve. So it looks deterministic for quite some while, and then there's an additional stochastic process on top. And this deterministic nature, this has been found by Gopal Bhatta et al. and they analyzed 20 gamma bright AGN. So they looked at the gamma ray light curves, and they found that Parks 1502 plus 106, our neutrino emitting AGN, is the most deterministic source of all. And this word deterministic, I think this is important, because I think it will play an important role for planning observations with the precision instrument ngEHT. A deterministic system is a system in which no randomness is involved in the development of future states of the system. Based on a detailed understanding of the system, the AGN, future states can be predicted. So we can say in which state the source will be. Knowing the deterministic phase of an AGN should allow also to study the stochastic contribution, which will of course be there. And we can then study the stochastic contribution in more detail. So knowing the deterministic phase of an AGL will enhance the success of the observations with the future ngEHT. A bit more on deterministic processes. I'm really thankful to Sarah for her talk and for mentioning and introducing already this. A deterministic process is, of course, a processing jet. So processing jet provides a deterministic scenario which can be predicted. So this is a game changer, I think, for observing AGN and for studying them in more detail. Jet precession has been found and modeled before in quite a number of sources. I list some of them here. The one indicated in red here is another neutrino emitting AGN, Texas 0506 plus 056. And of course, OJ287, and this has been mentioned by Sarah already. And I show the same plot as she showed from Zulema Abraham in Nature Astronomy. So the best explanation for these processing jets is either a supermassive binary black hole or the lens tearing effect of a viscous disk. It will be enormously impressive to detect a supermassive binary black holes, either with the EHT or the ngEHT. It would be fascinating to have gravitational waves formed with supermassive binary black holes. But I think this deterministic aspect is important. And I showed again OJ287, the deterministic showcase. I'm still convinced of the source. And what you see here is taken from our paper. So in the first two images, you see the jet is wandering in the sky. You can really see it in VLBI images. The jet is moving downwards and it's moving upwards again. So you can really see the precession there. We modeled this with precession and nutation, and then you can really model the kinematics of a so-called stationary jet feature. It's not stationary at all. If you look closely enough, it's moving based on precession and nutation. But that's not all. You can also predict, I think, the light curve, the flux density variability. This is the radio data for OJ287. And you see two different timescales. The longer timescale of 23 years corresponds to precession, and the shorter timescale of 1 year corresponds to nutation. So you can predict.
Silke, apologies to interrupt. You have 5 minutes.
Thanks. That's great. So this is my last slide already, so I can take a bit more time for this. So neutrino emission acts as a spotlight and shines a light on the astrophysics of jets. And based on the two neutrino emitters we analyzed so far, so two of the three where we had a closer look, we find that these sources are really special and unique. We find evidence for interaction, either interaction of jetted material or interaction of the precessing and curved jet with the narrow line region clouds. Evidence for precession in both sources. So these are binary black hole candidates and might be added to the list of Sarah. We find evidence for high polarization in Parks 1502 and evidence for the spine sheath scenario. And this is only part of what we found. So these are really unique sources. We find extreme conditions, but we think they are of deterministic nature. So the jet precession is a game changer. And because of this precession, different parts of the jet of the AGN are affected. So AGN variability and AGN kinematics can be predictable. And this is the message I want to bring over. Knowing the state of an AGN will be crucial for ngEHT observations in the future. So many thanks for your attention.
Silke, thank you very much, particularly for keeping to time. I've asked if, okay, we have 2 questions, 2 raised hands. So Aditya Tamar, please go ahead with your question. That'll be followed with a question from Sarah Markov.
Right, thank you. So my question concerns the initial mention of the IceCube collaboration in your talk. So in 2013 and 17, IceCube has been measuring the neutrino oscillations associated with the 2-flavor and the 3-flavor scenario. So whether the jet precession and the spine sheath or object basically that you're studying through AGNs, could it inform about those corresponding goals of IceCube in addressing things like the neutrino oscillations? Thank you.
Oh, that's a great question. That would be perfect if that would work, but I don't think that this knowledge about how an AGN works will help in determining more about the neutrino oscillations. But I might be wrong and not informed, so I'll have a look about this and I'll try to let you know later.
Thank you.
Okay, thank you. And Sarah?
So thanks a lot, Silke, for the talk. It's really exciting about this ring feature. I was curious, so you showed a light curve where, you know, there was this kind of exceptional radio emission around the time of the neutrino flare, but then there wasn't much gamma rays. And I was wondering, usually when you get neutrinos, you get gamma rays. So what's the interpretation of that in the context of this model?
Yeah, Sarah, that's an important point. There was a similar problem with Texas 0506 plus 056, that at the detection of the neutrino, of the one neutrino only, it was low in gamma rays. But then looking back into the archival data, it turned out that there were, I think, 11 more neutrinos generated at earlier times and seen in the archival data. And at that time, the gamma rays were high. And here in PAX 1502, the gamma rays are low and the radio emission is high. So I think this requires more modeling. So we are thinking whether the gamma rays are really low or whether they are absorbed. And that makes a difference in where the neutrino is created. So it's either the broadline region or beyond or the blazar zone. So this requires a more detailed modeling of all what we know, bringing everything together and then providing a proper model for this. But this is certainly an important point.
Okay, thank you. We have 45 seconds left. So one last question from Marshall Eubanks.
Yes, I was just going to ask about the flux. You detected one neutrino. How long do you think you have to wait to detect a second from this source?
Yeah, that's another good question. So I hope that the precession we find will help us. So there are already predictions based on our work for Texas 0506, where we claim that if the jet points in the right direction again, then neutrinos can be detected again. And other authors have picked it up and created a prediction on when the next neutrino will be generated. There's another point to this. The IceCube facility is being expanded and will become much more sensitive. So it might go to deeper levels of neutrino energy. So yeah, that will be interesting to see as well if that helps in detecting neutrinos from this source or from other sources as well.
Okay, thank you. Unfortunately, we have to move on. So we have another raised hand. If Resi Imami Maibodi, if you could contribute your question to the discussion session that will follow after the last talk. Silke, thank you very much.
Pleasure.
So now let's move to the last talk of this session, which will be presented by Alex Tetarenko from the East Asian Observatory. Alex, please.
Cool. Can you see my slides all right?
Yes, we can. Thank you.
Cool. Thanks. So good morning, afternoon, evening, everyone, depending on where you guys are at. In this talk, I want to discuss the science case and feasibility of studying accretion and jets in galactic X-ray binary systems with millimeter VLBI, in particular highlighting the prospects that a significantly enhanced ngEHT array could have for this kind of science. So before I get into all the cool science that we can do with X-ray binaries, I want to first just briefly backtrack a bit and try and motivate why it's important to understand jet phenomena in general, and why X-ray binaries, I think, are one of the best ways to do it. So determining how these kind of jets arise and quantifying the energy they carry, these are really important multifaceted problems in astronomy that can have a lot of implications for other fields of physics. And we've already seen this in quite a few talks yesterday and today. For instance, we know that these jets have a fundamental effect on their environment, where the injected energy can alter the chemistry of interstellar gas, in turn influencing large-scale processes such as star formation and even the evolution of entire galaxies. Additionally, these jets also come into play within the exciting new areas of multi-messenger astrophysics. Like we just heard, one of the most promising ultra-high energy neutrino candidates are actually the jets launched from supermassive black holes, as these jets can accelerate some of the most energetic particles in the universe, which when they interact with radiation and matter can create these exotic particles like neutrinos. Further, merging compact objects that produce gravitational waves can also produce powerful jetted outflows. So these jets are everywhere, but despite their prevalence and their clear importance in our universe, we still understand embarrassingly little about them and their fundamental properties. In particular, sort of some of the key unknowns that we're left with right now are, launching and acceleration mechanisms. What are the physical conditions actually look like in this key kind of launching acceleration zone? What actually governs jet production? Where do, black hole mass, spin, and accretion rate, what roles do they play? What causes jet evolution over different timescales? Where do magnetic fields come into play in this process? And of course, the energetics of these jets and how they can compare to other kind of feedback processes that we know about. So to start answering some of these questions, it doesn't mean that we necessarily have to be studying the big supermassive black holes, because it turns out that the smaller stellar mass ones that exist in X-ray binaries in our galaxy can actually be really ideal test beds for jet phenomena, because they're numerous, they're close to Earth, and they evolve on human timescales. So these systems in particular contain a stellar mass black hole accreting matter from a companion star, and just like their more massive counterparts, they launch these powerful relativistic jets. We tend to see two main types of jets observed in X-ray binary systems. We see these compact steady jets, as well as discrete jet ejections. Now, the compact jets are usually associated with a lower luminosity state where most of the accretion power predominantly comes out in the jets, while the discrete jet ejections tend to be launched at higher luminosities during a transition between a more jet-dominated and a more disk-dominated kind of accretion state. Now, as I just said, these systems evolve on human timescales, and by this I mean that the majority of these systems tend to be transient in nature, progressing from periods of minimal activity into these bright outbursting states on timescales of days to months. So we can essentially watch them change in real time. But we don't just have these transient versions of these systems. There also are quite a few that what we call persistent, which basically kind of remain in an outburst state for most of their lifetimes in these bright sort of accretion states. Now, again, like their more massive counterparts, X-ray binaries are also clearly broadband objects. They emit across the electromagnetic spectrum. And while the lines can get a bit blurred in some bands, for the most part, jet emission tends to dominate in the lower frequency bands, and emission from the accretion flow tends to dominate in the higher frequency bands. Now, with the compact jets in particular, we tend to get higher frequency emission from closer to the black hole. So when we're looking in a sub-millimetre regime, we're likely looking right in the sort of base of the jet type region. All right, so VLBI, as we all know, it's a powerful diagnostic tool that's been used to study supermassive black holes and their jets and active galactic nuclei for decades. And these extensive studies have allowed us to make measurements of key jet properties like kinematics, geometry, collimation profiles, morphology, all in turn providing really invaluable insight into jet formation and collimation processes. And of course, today's state-of-the-art global VLBI arrays are able to achieve tens of microarc-second resolution, enabling us to image down to these event horizon scales in some AGN sources. Now, black hole X-ray binaries within our own galaxy, they're located much closer to Earth than these extragalactic AGN sources, but their black holes are millions to billions of times smaller in mass. So that means that direct imaging on horizon scales is just not feasible. But global VLBI arrays can allow us to directly resolve their large-scale extended jets. And as I mentioned before, black hole X-ray binaries really do provide this sort of distinct advantage over AGN when it comes to accretion-driven jet research, because we are basically able to observe many more dynamical timescales and ejection cycles in these systems, and really just watch the jets and the accretion flow change in real time in a single system. Further, these kind of AGN and X-ray binary studies, they're not mutually exclusive, because as we think we know, accretion and jet physics are believed to, proceed in this kind of scale invariant way, where the processes that govern energy input and output can be normalized with black hole mass. So in that sense, knowledge gained from X-ray binary studies can be applied to AGN studies and vice versa. So we can get a much more complete kind of view of black hole jet physics when we view all of these different studies together. Now, when it comes to VLBI studies of X-ray binaries, we generally have two kind of main science goals. One is astrometry, and two is the direct imaging. So with astrometry, our goal is to get these model independent kind of parallax distances. And this is really important even in the era of Gaia, because while Gaia capabilities to conduct high precision astrometry of X-ray binaries in the galactic plane, it can be really limited due to high extinction and low optical brightness when these systems aren't in these bright outburst stages. And now being able to get distances to these systems is really important. It kind of has this really cool trickle down effect, because if we have a distance, we can actually make the connection between observed and physical parameters, flux and luminosity, angular and physical speeds. We need distance to be able to drive system parameters like black hole masses and spins and 3D space velocities. And on that note, knowing this velocity distribution of X-ray binaries at galactic plane crossing can also be used to determine potential kick velocities these systems may have actually received at the birth of a black hole, which can give us an indication of the birth mechanism of black hole, whether direct collapse or supernova. And on the slide here, I show you a really kind of recent example, really recent since it just came out last week, of that really kind of highlights the sort of domino effect of knowing the distance to these X-ray binary systems. So in this study by Miller Jones et al., we got a new refined distance to these X-ray binary systems, Cygnus X1. And one of this sort of kind of domino effect that came out of this was that with this new distance, it implied a much more massive black hole mass than we previously thought, which means that the progenitor star that actually produced the black hole in this system had to lose a lot less mass to stellar winds during its lifetime. So you can see that really awesome kind of domino effect of how just knowing the distance can tell us so many more things about the system. Now, of course, our other kind of science goal with VLBI studies of X-ray binaries is to sort of direct imaging, and in the same way as we've done for sort of AGN sources, with this direct imaging, we can look at morphologies and size scales, speeds, acceleration, energetics, jet orientation. We can even learn about the structure and dynamics of the accretion flow from looking at the effect that it has on these jets. But when it comes to X-ray binaries, so far, direct imaging studies of these jets with VLBI have mainly been focused on centimeter regime. So we're talking like less than 22 gigahertz. In particular, the compact jets have been resolved in a few systems and only along the direction of the jet axis, not perpendicular to it. While the jet ejection versions have been resolved with their motion kind of tracked over days to months in a handful of other systems. Now, in the centimeter regime, we're looking at like milliarc second scales, and at kiloparsec distances, this translates to something like 10 to the 8 gravitational radii. So still pretty far out from the black hole. All right, so to kind of give you an idea of where we're at in terms of, imaging and analysis with radio VLBI, I'll take you on a bit of a brief trip into the past first. So if you go back to the 90s, sort of the state of the art with this kind of science was you could observe, these systems and be able to distinguish changes in morphology on like daily to weekly timescales. That's what you see here on the left side of the slide, the system GRO J1655, where time goes from top to bottom. As you got into the 2000s, we started to be doing a little bit better and start to actually be able to see these changes on kind of like daily timescales. That's what you see here on the right. This is SS433 system. You see these ejections being ejected on these kind of daily timescales. But the thing is, these X-ray binaries, they're highly variable on even shorter timescales than days. And that's really kind of the big difference when comparing them to the supermassive black holes. They're changing so rapidly, evolving so rapidly that static images don't really cut it, simply because you start violating, this fundamental assumption about your synthesis that, your source isn't changing while you're imaging. So we need to be able to sample this kind of rapid evolution of these jets in the image domain on timescales as short as minutes. And we need the techniques to be able to do so. Now, with recent upgrades to current facilities, we've just within the last few years begun to start being able to do sort of a snapshot imaging approach. And that's what you see here on the slide. This is an example of VLBA observations at 15 gigahertz of the system V44 Cygni, where you can see that these snapshots are 2-minute snapshots in this movie. And you can see that we resolve and track many different jet ejections over this few-hour period. Now, while this kind of time-binning approach allowed us to really track the motion of all these components in real time, it also leads to a significant decrease in sensitivity in these small 2-minute time bins. Now, with V44 Cygni, it was super bright, so this wasn't too much of an issue. But if you have a source that's fainter and it's faster moving, you could run into this sort of situation where you're not only not detecting the source in these short kind of snapshot time bins, but also you may not even be able to detect the source in the full observation because it could be completely smeared out by these really large sort of proper motions. Now, recently we ran into this exact issue, and a colleague of mine, James Miller-Jones, and his student, Callan Wood, actually came up with this really cool sort of a new technique to kind of work around this. It was basically this kind of UV stacking technique. So what happens is you split up your observation into a large number of discrete time bins again, such that, in each time bin, the source is only moving over a small percentage of your beam. Now, the phase center of the UV data for the on-source observation in each time bin is then shifted according to this user-defined proper motion, so that the peak of the moving component appears in the same position relative to the phase center in the images from each time bin. And in this way, once you concatenate all of your time bins, you produce a single image whose phase center basically follows the component as it moves. And this allows you to produce a much more higher sensitivity image that isn't going to be smeared out because of the high proper motions. This is actually what you see here on the figure on the slide. The top panel is sort of an original image where you see component A marked there as a slow moving ejection. And then on the bottom panel, you'll see an image after it's been corrected with this UV stacking technique. Once again, you see component A, but you now see a newly detected fast moving component C here, which was lost in the noise in just the original image.
Alex, I apologize for the interruption. 5 minutes.
Sure, thank you. All right, so while radio VLBI has done a lot of extensive work in X-ray binaries, when it comes to the sub-millimeter, these studies are still very much in their infancy. And this is mainly where they're mainly confined to sort of unresolved photometric observations, whether this is time-resolved observations like you see here on the left of some flaring light curves from V44, or sorry, the right from V44 Cygni, or whether these are, sub-millimetre observations integrated over several hours to give you a single data point. For example, when doing sort of spectral energy distribution studies like you see here on the left. But the thing is, the sub-millimetre uniquely allows us to really isolate radiation produced by the compact jets from radiation produced in the accretion flow near the black hole, right in that key sort of launching and acceleration region. And for that reason, the sub-millimetre really represents a key observational anchor needed as well for the development of state-of-the-art theoretical models and simulations. So in these observations shown on the slide, we're using facilities like SMA, JCMT, NOEMA, all separately. But what if we can combine these into a millimeter VLBI array? What do we get then? Well, higher frequencies means we're getting to higher resolutions. So before I told you with radio VLBI, we can probe, scales about 10 to the 8 RG. With a millimeter VLBI, we can get down to about 10 to the 5, 10 to the 6 RG. Right, zooming in on that kind of jet-based region. Now, direct imaging in a sub-millimeter could then allow us to constrain, size scale of the emitting region, velocity of the jet flow through measuring proper motions of jet components, alignment of the jet axis through measuring the position angle of the jet components. We might actually, in some cases, we expect, there actually to be a misalignment between the orbital plane and the jet axis, which can reveal information not only about accretion flow dynamics, but also black hole formation mechanisms as well. From this kind of imaging, we could also get at morphologies and energetics. And even because we're looking at this really key sort of jet-based region, possibly even insights into the particle energy distribution and particle acceleration in that region as well. And that's just millimeter VLBI alone. But if we combine it with other multi-wavelength facilities and with theoretical work, for example, if we combine millimeter VLBI with previous direct imaging results at radio wavelengths, we can be able to start connecting the inner and outer jet regions to understand propagation and geometry of the jet flow. By combining millimeter VLBI with X-ray observations probing the accretion flow, we can start investigating the connection between the accretion flow properties and the inner jet structure. And then, of course, by incorporating new constraints from this millimeter VLBI imaging into cutting-edge theoretical modeling, we also can go further in that respect too.
2 minutes, Alex.
Yes. So, what facilities do we have available to us for this kind of work? Well, right now we have something like the GMVA, which can give us, the sort of intermediate frequency bands between the radio and the sub-millimeter, and then, of course, the EHT and the ngEHT. But how feasible is this actually? So there are a few major issues that we have to take into consideration, not complete deal breakers, but something that we have to consider. One, the transient nature of these systems. Well, there was some discussion yesterday about possibly, TOOs being an observing mode for a future ngEHT. Right now, this isn't really a possibility. But if we go after these sort of persistent X-ray binary systems that are always bright, always outbursting, we can get around that. Lower flux levels is an issue. But with new kind of passive phasing implemented at ALMA, for instance, we can get to hundreds of millijansky sources. So we can go get past that issue. We need availability of close bright calibrators. This is something we have to keep in mind, and of course, source visibility. We don't want something too low or too high in declination so that there's some facilities that we can't observe them with. Now, these first four, these are all basically target source limited. So if we pick our sources correctly, we can kind of get around that. And on the slide here is a couple of examples of a few sources that can get around all those issues. Now, the next one is UV coverage. So we want to be able to meet our science goals. We don't just need sensitivity, but we need the UV coverage to create high quality images. Now, this is an example of what the UV coverage would look like with the 2017 EHT array in black and an ngEHT array in red for full observation of those three target sources. But we're also interested in snapshot coverage. So here is an example of 15-minute snapshots of these systems as well in UV space. You can see that ngEHT allows us to actually sample this UV space significantly better.
Alex, I'm sorry, I'm going to have to ask you to wrap up.
I'm almost done. The last is just time variability. So because of the rapid evolution, we need to come up with really kind of clever techniques to extract science from these millimeter VLBI images, whether this is using snapshot imaging, whether this is using UV stacking technique that I told you about, or whether this is using this really kind of clever techniques like dynamic imaging or clever modeling techniques like used in the Themis package to try and actually be able to get real properties out of these images. That's going to be an important part. So I'll just pop up my summary there and just say that, you know, observing X-ray binaries with millimeter VLBI is definitely an ambitious project. It's definitely challenging, but it's certainly worth it in terms of exploring the science potential for making new discoveries in accretion-driven jets and outflows kind of science. And ngEHT is really going to help us overcome the observational hurdles with this sort of science. And we can be actually working on the analysis hurdles today with current data that we have in hand, as well as what we can obtain with today's millimeter VLBI arrays. So thank you very much.
Okay, thank you, Alex. Unfortunately, there's no time for questions now. We've overrun by a few minutes on this last talk. However, this session is immediately followed by a discussion session. So let me thank you, Alex, and thank all of the speakers in this session. Zlot, Paragi, you had your hand raised. Again, apologies to you if you could make your question in the next session. So let me close this session. Thank everybody for your presentations and questions, and let me hand over to Jose Gomez, who will now lead and moderate the open discussion session. Thank you very much.
Thank you very much, David. Thanks a lot. As you mentioned, we have now half an hour for discussions. So we had today a really nice. Let me just. Okay, just a second. Yeah. Okay, so we had today a really nice set of talks. We have been covering many different aspects. So we have talks from the Frank Eisenhower earlier today, Jonah Wash, Sarah Esplar, Nagar, Silke Britzen, and just now Alice Tetarenko. So there has been plenty of new exciting science opportunities, and I think the discussion will benefit a lot if we can comment about possible synergies with the ngEHT. So we have heard about efforts to find new targets for horizon science, the amazing stellar orbits determinations, the possibility to have hundreds of thousands of these stellar orbits to do amazing science and to study GR in Sajay. Also, we heard about how we can get better estimations of black hole masses in also nearby galaxies, and of course, very interesting talks about the binary black holes and how we can connect gravitational waves with ngEHT observations, and then to neutrinos, which is a new, very, very hot topic, and the associations with AGMs. And finally, Alice gave us a beautiful talk about possibilities to observe X-ray binaries. So really, very rapidly sources we can observe in few weeks what takes years in AGMs, and very rapidly. So we have an opportunity to test our imaging techniques for rapid variable sources like SAGE in X-ray binaries. So now is the time to ask the questions you had in mind that we didn't have time to cover before. And please, for that, raise your hand in Zoom, and also please consider using the chat in Zoom, and for longer discussions and more detailed discussions, please use Slack. So the floor is now open. So comments and questions for any of the previous speakers. there were some questions for you, Neil, about how did you get the fluxes and how many actual sources. So can you comment on that, perhaps?
Yeah, some of these I replied individually, yes, to I haven't got to Slack yet, but on the chat. The basic idea is that, again, for example, in fact, one, I should immediately say I answered Gopal's questions wrong. I somehow heard flux instead of resolution. Gopal had asked about 230 gigahertz versus 345 gigahertz EHT or ngEHT. And so in some of my figures, I've used both. The solid line was 230 gigahertz resolution and a dashed line for 345 gigahertz resolution. But in some figures where I just used a salmon and a green colored area, that was always the 345 gigahertz resolution. So at some level, it doesn't get better with 345 gigahertz because I'm already using 345 gigahertz. There's, as Shep points out, and several others, Gopal also, there's this potential of 690 gigahertz from the ground, which would then tweak up the resolution even more. And then, yes, some objects could cross the line and get resolved in black hole rings. But I guess the dominant factor here would be any random errors in the black hole mass estimates. Even though the error bars look small, those are the quoted error bars. And as we've seen very often between different methods, there seem to be errors that are larger than the intrinsic quoted errors. So yes, objects will move around, and even the lines are a little blurred, not only because whether I use 230 gigahertz or 345, but as you know, as the imaging working group is gaining so much experience, their so-called super resolution, or Avery and so many other people who are using super resolution in models. So I guess these dividing lines are kind of blurred, and yes, things will move around, which is promising to me at least. If of the 10 objects, if 5 move up and 5 move down in black hole mass, that would be perfect because we want those few that move up.
Yeah.
The other question was the 230 gigahertz. Yes. So or 345. Yes, it's true that very few have GMVA observations. Only about 300 sources have GMVA. And so when I take the spectral index from a lower point from 43 or 8.4, as I mentioned as I showed in that plot, they kind of go all over the place. And in part, it's my fault. For example, just taking some of these large databases like the radio frequency catalog, it gives you a flux on a long baseline. It doesn't give you an epoch or a telescope or an idea of a resolution. I kind of fudge it. If it's very south, I assume it's LBA. If it's north, I assume VLBA, and kind of, you don't know if it's a snapshot with an elongated beam or not. So I've done a few fudges, but it's just suboptimal. And here, surveys like the KVN is doing, multi-frequency simultaneous surveys would be, and they have catalogs already, and we definitely need to talk with them. That would help really clean up a lot of the sample to detect, to really hone in on the ones that are truly flat and which we have a better chance of getting into to the EHT.
I'm sure you will find new excellent candidates. I have no doubts. So we have more questions here. Rasia, you have your hand raised.
Yeah. Hi, very nice talks. All of them in the morning. So I have a few questions from different people, if that's allowed. Can I do?
Sure.
Yeah. So let me start with Jonna Walsh, if she is around.
Hey, yeah, I'm here.
Oh yeah, hi, very, very excellent talk. I just have a question that I think I also posted in the chat window. So that's about the possibility of actually getting information about AGN activities of PGC 12557. So I remember that you actually said a lot of nice things about the fact that it could be a relic of the red nugget, from like redshift of 2 and so on, and also the black hole mass, etc. But just wondering, do you have any information at all about its AGN activities and its comparison between like the early top galaxies versus the late top galaxies? Can we compare them off together?
Yeah, so for PGC 12557, there are some Chandra observations of it. So it is detected in X-rays, but this is not like a booming, like bona fide AGN. So when you look at the NIF spectra, we're not seeing strong evidence for the AGN there. So the continuum looks very normal. Like, the absorption lines are very clearly there and are not being washed out. There are no emission lines in the AGN, in the NIF spectra. So, I mean, while there is an AGN there, it's not, like I said, this bona fide AGN. And yeah, I mean, definitely comparing these like early type galaxies to late type galaxies, it makes doing stellar dynamical modeling a lot easier for the early type galaxies because they usually are quiescent galaxies and don't have like these booming AGN like the late type galaxies do. So moving and looking more toward modeling through stellar dynamics and gas dynamics, the late type galaxies, it's definitely a challenge to overcome, is trying to deal with that AGN contamination so that you can actually reliably measure both the stellar and gas kinematics right at the center where, we're most interested in.
Okay, very excellent. And does that help us to understand that this is really a relic when you're saying that it seems like PGC 2F547 doesn't have too much of the ongoing AGN activities? All right, I just realized about actually the assembly history of that particular galaxy by looking at the AGN activities, if at all.
Yeah, so the reason why we think it might be a relic is actually, I didn't have time to go into all of that, but it's more looking at the galaxy, the host galaxy itself. So besides being small and like compact, so a small effective radii for its given stellar mass, like it's very consistent with the redshift 2 mass size relation and not, the redshift 0 mass size relation. When you look, I mean, as you also saw in the velocity maps that I showed, it is rotating, so it's a fast rotator, and that's consistent with the diski-like structures that are seen at higher redshift for the redshift 2 red nuggets. Also, if you look at the stellar populations of this galaxy, but also the, in general, the sample of galaxies that, look similar to it. So the stellar populations, they're made up of uniformly old stellar ages, and that's over the extent of the galaxy, so out to even a couple of effective radii. So these are stellar ages that are about 10 gig years. So kind of the picture seems to kind of fall into place. Now, can we say they're absolutely 100% relics or completely pristine relics? I mean, that's probably a little bit of a stretch, but I think they're definitely an interesting population of galaxies to study.
Thank you so much. And can I continue? Just
let's do a round, and then at the end, if you want to, you can also ask. And please feel free to use also the chat in Zoom. Okay.
Okay. Yeah.
Sure. I think the next one was Marsha Evans. I think you had a question. You had your hand raised.
Yes, I just had a question about these galactic objects. We saw the very nice SS433 video, and if you calculate those things, you get that the black hole shadows should be on the order of nano arc seconds, 10 to the minus 15, 10 to the minus 16 radians. And the question I had was, well, what can the Event Horizon Telescope possibly do, or its ngEHT possibly do for these galactic objects?
Yeah, that's an excellent question. So yeah, we have no hope of ever, imaging on horizon scales for X-ray binaries, but the EHT today and an ngEHT can allow us to really image these jets into this sort of key jet-based region that we can't get to with radio frequencies, where we're probing much farther out. So that's really the advantage that we get for looking at these X-ray binary systems. Yeah. Unfortunately, never able to really get down to the horizon scales, but we can still get a pretty good view of this sort of inner jet-based region where the particles are first being accelerated in the jets. Yeah.
Thanks.
I think Alex, I'm sorry, Andrei Lobanov, you have a question?
Yes, thanks. I wanted to ask about the nanograph, Sarah Burke, if Sarah, if you're still there. She's probably not. Okay, then it's passed. What I wanted to say about the binary black holes, in addition to that question, there's an interesting thing that many of those candidates for the gravitational wave signal may not necessarily be active, because the modeling and some predictions show that basically if you have systems with the nearly equal mass black holes, they would effectively or efficiently destroy accretion disk around each other, and then will be quiescent for a large period of time on the small orbital separation. So that's when they're going to be detectable by nanograph and other gravitational wave detectors. So that's an additional complication there, because people are typically looking for some AGN type of objects as potential candidates, but it may not always be the case. So that's what I wanted to ask Sarah about. Thanks.
Thanks, Andre. Sarah, I'm not sure she's not here. I didn't.
No,
she's not. Sorry about that, Andre. Yeah, that's an excellent point. I guess, Andre, that another thing we could look at is, is the optical, light curves and see if there is any periodicity there. But as you say, the AGN may be quite quiet. But that's an excellent point. Razi, do you want to ask again?
Oh, hi. Yeah, that's a great pleasure. So I have a question for Silke Britzen, if I'm right in spelling their name, actually. So that was very beautiful, the ring of neutrinos that they're actually seeing from this processing jet. I was wondering, is there any chances that we can also look for electron-positron pairs in the ring? And just, and also sequel-polarization that I think she has found, especially for the sequel-polarization, it could be, but, but generally speaking for the others as well.
I think that's an interesting question to look for circular polarization in this source. I think the magnetic field plays an important role in the ring structure and in the source in general. So, and it will be interesting to see how this magnetic field interacts with the processing jet and what role it plays in this layer the scenario. So I think it would be a good candidate to have a look for circular polarization in this source. But yeah, at the moment, I cannot say more. It requires more modeling, it requires more observations, but it's certainly an interesting point concerning circular polarization.
Okay, thank you.
Janelle, I was thinking that, as you know, in the HT paper, we found that the mass of M87 was consistent with the stellar dynamics, but not so much with the gas dynamics. So, do you see any prospects for using the future ngEHT measurements to calibrate or refine the dynamical studies of supermassive black hole masses?
So this is what, and I guess we also heard some very interesting results from Janelle. This is definitely what we want to do. As I mentioned, as a first step, this is about 3 years ago, we asked for M87 NewsAO results to work the other way, right? Because we had a certain supported black hole mass, and we've heard the explanations of why gas kinematics can be, ionized gas kinematics can be bad. So these NewsAO, this is with Karin Gultekin and Karl Gebhardt. We've been waiting, it's been in the queue ever so long. It arrived yesterday, I still haven't seen the data. The idea with Muse, of course, is that you get the whole optical range pretty much, many ionized species lines and very good stars, much higher signal to noise than STIS over IFU rather than individual slits, but with some a slightly lower spectral resolution. But with the signal to noise, I'm sure we could center better. So we'll start with this part on the first side, which is since we now have stellar and ionized gas kinematics all in the same data set, plus the ideas that Britzen, ngEHT, and Avery have come in with, and Janelle also mentioned a bit of this, thicker disks, if it's an outflow or if it's subcat layering rotation, we could try to fit all of this and see if we can come to an example. Of course, that's one source. So we were doing just very specific sources, so not as large as what Janelle is doing because we've only recently started. We have two others which are very, very good measurements in the optical, in CO, 1% errors in CO, which we then also asked for MuseAO so that we can cross-correlate that method, ionized gas stars versus CO. Now, if we can understand these systematics, it helps coming to the point of what you're making, which is if we now get, it depends on how consistent all these results come out and whether we can get a clean solution within all of these programs, which are just molecular gas, ionized gas, and stars. But if, and as Avi very correctly says, with these super resolution techniques, I've been very, very careful when I showed the limits that, we can't do any more rings from the ground. But if it's true that we can do in this modeling and in this imaging some super resolution techniques, we could get 5 more, maybe 10 more. According to the graph at this point, there are 10 more rings that we could get. At least a black hole mass measurement, if not directly an image. Those 10 can be very, very critical because the errors that we get are so model independent at some level, and the precision is so much higher. But it remains to be seen how the other groups will do, right? Perhaps some of this problem will be solved already with the ground-based non-ngEHT data. I suspect not. If you could get 10 black hole masses for those 10 critical things, which will then follow up in all of the others, I think that would be a very useful constraint, because eventually we're taking this relationship and applying it to the universe. And there are clearly so many systematics.
Yeah, absolutely. Yeah, the possibility of doing the modeling, not just imaging, it's huge. So this is quite very exciting. Shep, I think you have a question.
Yeah, thanks a lot for these talks are great. And one of the things that we want to focus on in the ngEHT is getting new sources, of course. That's what we're discussing. I'm wondering if people have thought about, maybe Neil or someone has thought about the optical depth of these new sources. And the reason I ask that is that Sag star has an Eddington rate of 10 to the minus 8, maybe. M87 might be 10 to the minus 4. They're very different masses. When you get very close to the black hole, are there issues of optical depth that might prevent these new sources from being letting us see all the way down to the event horizon? Are M87 and Sag are special cases where we can see all the way down?
Is Venki on? At least.
Yes, I'm here. Yep. So yes. Yeah, we do have. Yeah, we are working on some of these sources, and we have multi-frequency observations for at least a half a dozen of these sources, and we are expecting probably some of the GMB observations to complement the studies. And this is exactly along the lines of what we are trying to do, and it will, of course, make the science case even stronger for the from the ngEHT perspective. But of course, the first thing to do is we are working on the most prominent ones for the time being. But once we distill our source list, I think we'll get a much larger sources where we might be able to get a better handle on the opacity thresholds.
Yes, Michael, you have your hand raised.
Yeah, kind of on the same line. I guess this is a question for Neil and Janelle. We have many pathways to detecting some of these new sources. We can improve our angular resolution. We can try to push down to lower flux limits, maybe orders of magnitude lower. We could do long duration monitoring. And that's critical for binaries, let's say, and maybe for the other sources, we're waiting until a faint one becomes bright. We have modes like TOO. Which of these is your intuition for which is the most important to focus on? And how close are we to defining sort of hard limits for the ngEHT? And sort of associated with that, how many new sources would we have to get a mass estimate for this to be a primary science driver for the array and to really determine our baseline architecture? Or do you think this is just going to be a nice tangential sort of commensal capability, but it's not going to define whether or not the array is successful?
This is for someone else, right?
No, Neil, this is you. And I guess I'm just wondering, kind of your intuition. Are you close to answers here, or is this something where we need to really dig in?
You and Shep and Avery, because I've heard these discussions before, would be like honing in on, because you have that. I mean, three of you have so much more background and experience and the reality of the situation. What I will mention is something that Avery brought up in the Slack is if the techniques could get to 10 times better than intrinsic resolution, right? Because all of the plots I've made were intrinsic 22 micro arc seconds. So even if you forget space, I mean, just to give you a number and then you tell me if this is worth as a science driver or not. If we could get to 10 times intrinsic resolution to do some of these measurements, we're talking about 10 additional galaxies that could be done just from the ground. And then if you go to geo, would be 50 more, right? This is assuming now that you're getting something like 2 to 3 micro-arc-second resolution on the ground, equivalent through all of the modeling and new techniques. To me, at least, that sounds like a big driver, right? Because, but again, as I mentioned, we know so many, and perhaps Jonelle is here and can give us a much better idea on all of these systematics and whether she feels that some of these systematics can be just fixed from some of these large programs that she's doing, or whether your feeling is that there's going to be more things to do.
Yeah, I mean, oh, sorry.
Please, go ahead.
Yeah, so I mean, I think having these independent measurements from ngEHT, I mean, I think they're absolutely needed. I mean, we currently, in doing this just within dynamical methods, there are just not that many at all. And even, you know, people measure black hole masses repeatedly in the same object, and it's like, you know, it changes with time, not because of anything with the source, but just in improvements in data and modeling. And so just having, you know, even another, I mean, 50 sounds amazing to me, like having 50 independent black hole mass measurements to go with what we are finding from dynamics would be fabulous. And yeah, I mean, that sounds like a significant impact to me.
Thanks, Janelle. Yes, we are running into the a small break, but there are 2 people with their hands raised. So let's answer this, and then we move to the break. The first one is Gopu Market. Would you like, please, to ask something?
Oh, yeah, thank you, Jose. So this is to Silke, Britzen. I mean, this is about your argument that if there are deterministic way to characterize the jet, and if they interact with the BLR or NLR areas that can produce this, you know, neutrinos, if and even if those are very far away sources, but in that case, do you expect something from OJ287? Just curious. Neutrinos.
Can you? I got part of it, but not the whole question. So.
Do we expect high energy neutrinos from OJ287? At least we know, you know, the deterministic nature of its jet. So
okay, now I understand your question. No, I don't think we expect neutrinos from OJ287. I just put it at the end of the talk and in connection to Parks 1502, because both have a strong deterministic contribution. So Parks 1502 is the most deterministic source among 20 gamma bright AGN, and OJ287 is just predictable from the precession. You can explain the kinematics and the light curve in the optical and in the radio. So this is predictable, and this is what I call deterministic. But I wouldn't expect neutrinos from OJ287 from all what I know about these processes so far. But for Parks 1502 or sources like Texas 0506 plus 056, it's a different, there are different conditions in these sources. They are more extreme, and they have this stochastic contribution in addition. So there is clearly flux coming from the core region, which is not predictable. So you have a combination of deterministic and stochastic. And I do not see this in OJ287. And therefore, I make a distinction between these 2 kinds of sources.
Andre, last question.
I wanted to come back to the source selections, to the question to Neil. Neil, if you don't like the question, just return it to Michael and tell him, ask him how many sources do you need for the success of the EHT and ngEHT. But on the selection, I think you could basically do the combination of Korean VLBI network or high frequency VLBI visibility flux density measurements, and maybe even higher frequency total flux density measurements to weed out some potential candidates which would have very high opacity, as Shep was mentioning. And I think these two methods would give you the radio part of the sample rather reliably. And then you can get the optical measurements to get the black hole masses. Of course, there's an additional complication that we saw that in many of the radio loud objects, some of the broad lines can actually be generated by in and out flows. So it's actually shown in one of the presentations today also. So that would lead to in sort of overestimating the black hole mass from the broad lines. But this is the how we have to live with that potential bias anyway. But I think with just combination of KVM measurements and total flux density measurements at even higher frequencies, plus the optical measurements of the black hole masses, will give you a reasonably reliable sample of potential targets. Over.
Thanks, Andre. Yeah.
Yeah, excellent point, Andre. Okay, so thank you very much for your participation. We had a really amazing set of thoughts, and I'm really glad to see, you know, the general community very much interested in ngEHT synergy opportunities. This is indeed an excellent opportunity for everybody to find these common you know, targets and common science among different teams. So thank you very much for your participation, and now we have a small break, and then we continue with the sessions